I decided to talk about a very recent, well, we've been thinking about it for a while, but it's not really very formalized paper, which is joint work with Brendan Lucier, Marcus Mobius, and James Siderius. And it's part of this research agenda that I've discussed, probably maybe you've heard me discuss it before, which I like to think of as data, the fundamental particle of economics. And so the research agenda notes that a lot of economics, especially Bayesian rationality, is premised on this idea that people or decision makers, agents in our games, they have some access to priors or distributions over how they think the world works. And then when they take an action, or make strategic choices, they make these choices in a way that is going to maximize their expected utility when the state of the world is drawn from this prior that they have. Okay, so that's kind of a caricature of the classic economic setup. But of course, we're in a meeting on behavioral economics. And so I wanted to point out that the world doesn't really work this way. Even in big firms like Microsoft, where I work, you don't talk to the people implementing, say, the ad auctions and have them tell you what their prior is and how they tune their reserve price to that prior. Rather, they have massive data sets, and they look at these data sets and then they make some decisions about what to do. And I don't think anybody can really precisely formulate what their prior is about the values of the advertisers. And this happens, in many different company settings. This data here is bids for the EU ETS allocating carbon licenses. And so they look at historical data to try and determine how to run their auction in future years. And I'm sure you can come up with many examples of this on your own. And so there's this perspective that even very rational firms are making decisions from data sets and potentially not using these data sets to update priors, but rather taking them at face value. But what I wanted to focus on, or what I believe, is that this isn't just a property of firms that have access to lots of data, but this also is a property of human behavior. And so I think that the way, and there's some psychology books suggesting that the way that humans behave is that we walk around and we have experiences, and then we remember these experiences and we draw inferences on them when we're faced by similar situations in the future. So this is, for example, a lovely coffee I had in Stockholm, looking out on the lake there with a little yogurt parfait. And I have in my head a memory of this experience, an anecdote of drinking coffee in Stockholm. And when I think about it, I've stored sort of the whole experience in my head. I think about things like the coffee, it was pretty good. It really hit the spot. The menu, the options were healthy. The view is gorgeous. There was a dog at the table next to me, which was very cute. These kinds of things, these constitute the experience that I had. And so, then when and this is in contrast to storing something like the average quality of the coffees I had in Stockholm. Instead, I store these kinds of stories about all the coffees I've had in Stockholm. And then if somebody later on wants to ask me about how good is the coffee, I'm thinking of taking a trip to Stockholm, but I'm a huge coffee snob. How good is the coffee in Stockholm? I can draw back on all of these experiences and come up with some answer to their question. And so this is the way in which I think a lot of decision makers view the world. And it's a good model, especially of decision makers that aren't experts in the setting in which they're acting. So, experts definitely form beliefs and then fit models to capture some underlying state. If you're, working at the Fed trying to decide whether to raise interest rates or lower them, you have some some beliefs about how the world works, and you have some how the economy works, and you fit some models to try and understand if the economy is running too hot and so on. But non-experts lack models of the world, and so instead we store these anecdotes about like coffee in Stockholm, and then form guesses about the state upon demand when we're asked for it. Another reason that anecdotes might be particularly prevalent in decision-making behaviors is that you might not really know what question you're facing or what data you're allowed to keep. So for the first, if you're going to be asked about the quality of coffee in Stockholm in the future, you might do the extra work to just kind of keep some accounting in your head about the quality of coffee and aggregate answers over time. But maybe my friend that's taking a vacation in Stockholm is bringing her puppy, and she wants to know how dog-friendly are coffee shops in Stockholm. And I had no idea I would ever be asked about that. But because I've stored the experience and not just this single data aggregated data of the quality of the coffee, I can access that unknown and answer her question. Another point here is that there might be some kind of privacy or data provenance concerns that require decision makers to be able to forget things. And this, I think, is maybe more prevalent in the case of firms. So you could think about laws like GDPR, which give people the right to be forgotten. That is, I should be able to extract my data from a data set and have that not just my data point extracted, but furthermore, all the metadata that was computed with my data point as a part of it. And so the model I will introduce is one way to guarantee this kind of ability of removing data from the data set. So to just present sort of the overall model in this research agenda a little bit more precisely, what I'm imagining is that there is a state of the world theta. This isn't drawn from a prior, or it could be, but the theta itself, the class of priors from which it's drawn, this is all unknown to agents. Theta is just some unknown state of the world, and it's possibly high dimensional. This is the sort of coffee experience in Stockholm. And then what happens is that there's a bunch of anecdotes that are sampled from this state of the world. An anecdote is, you can think about it as a data point living in the same space as the state of the world. And it's centered around the state of the world, but it's a noisy estimate of it. It's a noisy observation. So an anecdote is the state of the world plus some zero mean noise drawn from a known prior or a known class of priors. And so using this model as the basis of the strategic decision-making on the parts of the agents in a game, we can revisit a bunch of classic models in economic theory. I'll talk today about decision theory. Let me return to that in a moment. But this kind of thought process of people reacting as sort of statisticians to data comes up in communication and persuasion games, where it helps us understand things like bias and polarization. It comes up in mechanism design space. There's a long history of work in this community looking at mechanisms, the designer constructing the mechanism and the rules of the mechanism using data samples. But also more recently, we see a bunch of work thinking about agents reacting to mechanisms, taking data kind of at face value, and how would we create mechanisms for such agents. And using this framing helps us understand how to design robust and transparent markets in these settings. But today I want to focus on an example of this agenda in the context of decision theory. And here, probably the most related work to the paper I'm going to discuss today is Andrea Wilson's 2014 job market paper, which you can find in Econometrica. I won't dwell on it here, but I just wanted to call it out because I think it's a really beautiful paper, especially for people from this community that are used to thinking about things like random walks and states and stuff like that. So please go check that out. So what I want to look at is this kind of question of people, agents, decision makers using anecdotes instead of priors, so their model of the world is an anecdote, how much memory do they need to make good decisions? So I'm going to think about a model where you have experiences over the course of your life. How forgetful can you be and still make good decisions in your life? And this is a big issue for me, so very, very personally important. And what we'll see is that you don't actually need all that much memory if you can be strategic about what you forget. And we'll see that the way in which you're strategic about what you forget is reminiscent of a very well-documented effect in behavioral economics called confirmation bias. That is, I'm happier, or I believe more, listen more, remember more accurately things that are closer to my current belief system. So let's look into the model of the paper. How do agents make decisions, and how good are those decisions? So we're going to set up a model in which anecdotes arrive over time. And the anecdotes are drawn, each one is drawn from some IID from some stationary distribution F. And F is, you can think of as parameterized by the state of the world. So these anecdotes ST are noisy representations of the state of the world. At every point in time t, I'm going to have a state, a memory state. And that's the set of things I'm storing at time t. It's a subset of everything I've seen up until that time. And at time t, I have to decide whether I'm going to remember this new experience I just had ST or forget it forever. So this is like an online algorithm. It's or streaming algorithm. It's take it or leave it. And then at some future point in time, capital T, the process stops and I am asked to announce an estimate. And for the purpose of this talk, I'll assume that what I'm trying to estimate is the mean of the distribution F. So I must announce, based on what's in my memory, I have to pick some estimate theta hat of the mean. As I said, this estimate has to be a function of what's in your memory, so you can't access stuff that you saw before. And furthermore, the memory itself is, well, obviously it can only store anecdotes. That's the whole basis of the model. So it can't store like a running average. And it can't store an arbitrary number of anecdotes. So I'm interested in how much memory we need to make good decisions. So the assumption here is that the number of anecdotes I can remember is bounded by some M. And some of my models will also assume recency, although not all of them. So here, the idea is that I can only remember anecdotes that happen to, my memory degrades as I get older. And those of you that are grad students might not realize this yet, but like, you're not going to remember what happened to you yesterday when you're my age. And so there's some K, and you can only remember up to K experiences from the past K days. And then what we're asking about is the quality of the estimate. So we're going to use a squared loss and ask about how can you design your memory system in order to minimize the squared loss between your estimate and the actual state of the world. And so one thing, what would be a good result here? You can ask how good, you're already tying your hands behind your back because you can only remember anecdotes. So how good could you do if you had perfect memory? You couldn't do perfect, but by central limit theorem, you can do pretty good. In fact, you can see that if you had perfect memory, you could remember all capital T things that ever happened to you. Then by central limit theorem, the empirical mean of capital T anecdotes is going to have squared loss like order 1 over T. And by Kremer-Rao, no other estimator can do better. So you should just remember everything. And then when you're asked to guess, take the empirical mean. Now, the interesting question for us was, what happens if you had bounded memory? And one thing you might naturally try is, well, I could just remember the most recent things that happened to me. And it's not hard to see that then you're getting a random sample of size M from the distribution F. And in order to match the accuracy of the perfect memory person, you would need to remember on order T anecdotes. So it doesn't help you save memory at all if you're just going to remember the most recent ones. Instead, what you should do is you should strategically choose what to remember and what to forget. And if you do that well, we'll show that you can achieve the loss that's equal to that of the optimal perfect memory person with memory that's just logarithmic in the number of time in the time horizon t. So here's the formal statement of the theorem for those of you that like to see the formal statement. We can fix any epsilon, that's going to be the error we're targeting. Then there's an algorithm for a decision maker with bounded memory, and this algorithm turns out to not need to remember things too far in the past, such that if the time horizon is large enough, like 1 over epsilon, and the memory is like log 1 over epsilon, then your error is going to be at most epsilon. And there's some assumptions on the the noise distributions here that I'm not going to go into. They play a role in the constants in this theorem statement. So in order
Nicole,
to...
can I ask a quick clarifying question?
Yes.
So do you force the estimator to be the empirical mean estimator?
What?
Do you force the estimator to be empirical mean estimator, theta hat?
Do I force the estimator to be
The empirical mean estimator.
Empirical mean, sorry. No, you can pick, and we have a lower bound where we allow you to try a different estimator.
And is the empirical mean estimator still the best given your choice of online algorithm?
Yes.
Okay. Thanks.
So I will show you the intuition of the algorithm using a very, very limited memory size 2. And I think that this is maybe the most interesting few slides from a behavioral economics standpoint, because it feels like it gets at an explanation of confirmation bias in my mind, at least. Okay, so we have this model, we have these incoming anecdotes, and you have your memory of size 2. And I'm going to divide this memory into the long-term part and the short-term part. And so there's the long-term part, what the memory I store there, I'll call X. There's the short-term part, the memory there, I'll call Y. So I get this incoming anecdote ST, and I have potentially 2 things in my memory, and I have to decide whether to kick them out and keep ST, or kick one of them out and keep ST, or to keep going. And then at the end of time, my estimate will be the long-term memory, or I guess now I'm contradicting what I told Rod a second ago, but this could be the average of the 2. It won't make much difference. So when to forget, like how are we going to decide how to forget? And what we're going to do is you can think about this long-term memory, and I realize I didn't update the notation in this slide, so ignore what's written, but we have this long-term memory X and we have a short-term memory Y. And so the short-term memory, remember these are both drawn from some F, right? Which is single peaked. And the short-term memory is going to be biased towards the peak of the distribution. So it's telling me what direction to move in. I want to update my memories such that I'm moving in the direction of Y, the short-term memory. And so if this incoming anecdote ST is in the same side of X as Y is, it's telling me that I should try and move in that direction. I should try and update my belief system such that it's a little bit more, say, to the right of the long-term memory X. And then once you realize that, you think, okay, so if I have 2 samples that are both to the right of my long-term memory, I should clearly move my memory state to be to the right. And so I should maybe kick out, say, everything in my memory and just remember my new experience. And that sounds like a good idea, but of course the problem with this is that you might be jumping around a lot. And so you need to not just move to the right, but you need to move to the right by not too far, or you're going to overshoot the peak of the distribution. And so that's where this idea that you can't replace your memory with your new experience unless it's close enough to your current experience is this idea of confirmation bias. And I'll sort of give you the proof sketch in a moment, but before doing that, let me just show you some simulations of this algorithm so that we can see the importance of confirmation bias in this algorithm. So here we're calling this Greek letter that I can never remember the name of, the step size, and or the like degree of confirmation bias that the agent has. And what I'm plotting is for that step size, the distribution of the estimate of the agent at different time horizons t. And so what you can see is when that step size is very small, the belief never really moves very much because you need to wait a super long time to get something that's close enough to your current belief in order to move you a little bit more. And so that's, if you're too biased towards your current beliefs, you're just never going to learn. It'll take you forever to learn. If you are too permissive of new experiences, of remembering new experiences, then you're going to jump around the peak of the distribution a lot. So you're going to jump way to the right, way to the left, basically every incoming memory you take. At first, that helps you get towards the peak. So you can see the blue and red lines for t=1 and t=2. I'm moving in the right direction. But then when I get close to the peak at 10 and 20, I don't get any closer. I just keep buzzing around. And so in order to actually learn, I need to pick the right amount of confirmation bias. And here is a plot that shows what happens with step size 0.7. So in order to show that this algorithm works, again, what I'm trying to it turns out that it's not as good as the perfect memory person, but I'm slowly moving towards our optimal algorithm. But what we can show is that you get something like 1 over epsilon, like polynomial in 1 over epsilon. After that much time, you're able to learn, get to epsilon loss with memory size 2. And we think that this is the best you can do, but that proof's a little bit hairy, and so we're not super confident in it. But it has this interpretation that's kind of what I talked through a moment before, that you take this long-term memory state and you try to take a biased random walk towards the peak of your distribution. The step size or the confirmation bias of that the human decision maker is feeling, that induces an expected step size in this biased random walk. And the drift is, this biased random walk is always towards the peak of the distribution. And so you can bound how long it takes you to get inside this epsilon confidence interval. And then once you're there, you argue that you're likely to stay there. And so you can turn this into a formal proof of the constant memory bound that we list here. But of course, the optimal is a 1 over t with perfect memory. And in fact, you can get that if you have memory that's logarithmic in the time horizon t. And the way that we do that is through an algorithm that mimics stochastic gradient descent. And so what I'm going to slightly change the model now for convenience of stating the algorithm. It's just a constant difference in the memory size. I'm going to assume at every time t, the decision maker gets a batch of m anecdotes, where m is the memory size. And then I'm going to basically write down the natural generalization of that short long-term memory algorithm I presented a few slides ago. I have in memory some subset of anecdotes. I'm going to use them to compute a current estimate xt. That plays the role of the long-term memory. Then this incoming batch, I'm going to split it in half. The left half, I'm going to use as in the role of the short-term memory. So I'm going to look at the average of the left half yt. that tells me the direction I want to move in, yt minus xt minus 1. That's the direction I want to move in. And I'm going to pick a step size and try to move in that direction. So that gives me where I would like to go, zt. Now, of course, I can't go to zt directly because I can't store arbitrary numbers. I have to pick a subset of anecdotes. And so I'm going to take the right half of my batch and look for a subset of anecdotes that whose average is as close as possible to zt. And the key here to getting this log is that there's exponentially many subsets that I could pick from. Of course, they're correlated, so we have to deal with that, but there's exponentially many of them, and so I should be able to get close to ZT with just a logarithmic memory size. So that's the algorithm. I'm running short on time, so I will just gloss over the proof sketch. It's basically mimicking, as I said, stochastic gradient descent. You can think about this yt minus xt minus 1 as the gradient of the squared loss function. And you can think about the zt as where you want to go. And so if we could go exactly to zt, this would be straight up stochastic gradient descent, which implies that after t rounds, our loss is order 1 over t. Now, we can't go exactly to zt, but you can show that this standard analysis is robust to small adversarial noise. So all we need to show is we get close enough. And since, as I said, there are exponentially many subsets that we can pick from, that's enough to show that we can get close enough to zt in each time step t. As I mentioned, we have a lower bound. I won't have time to present this, but it's basically based on a setting where the state of the world, the anecdotes are drawn from a Gaussian centered at the state of the world. And it assumes that you have this recency constraint. With those assumptions, it's enough to show that you have a constant probability of an error that's more than epsilon, no matter how long you try to learn. And the proof has a clever trick in it. So I will leave that tantalizing bit for you to check in the paper when it exists. But let me just conclude so that we can end on time. So what I showed was, I think, a step towards bridging behavioral economics and psych with a CS econ perspective on behavioral biases. We have this model of anecdotes as a basis for decision-making, procedure for learning, the mean of a distribution from anecdotes with bounded memory and inability to remember the distant past that does as well as perfect memory. And that algorithm demonstrates a rationale for confirmation bias. We also are able to extend these algorithmic results to multidimensional states. I was looking at a single dimensional one in this talk, or other inference problems like linear regression. And I think this points towards an interesting direction for future work, which is to look at different types of behavioral biases in economics and see to what extent they're aligned with optimal or approximately optimal algorithms in computer science, and use that as a sort of way to reason about the rationale for these behavioral biases. And let me just leave you with this broader research agenda, which I think is a pretty exciting path forward for economics and computer science. Thank you.